Okay, Toby, it's me who's going to do the intro. So, hello, everybody. This is, again, IronBeetle after a short break for the System Distributed Conference. And I'm excited to announce that we, again, are going to do this together with my colleague, Toby. So, we are going to continue our investigation of IronBeetle practical pragmatic consensus implementation right from that point where we started, where we stopped a month ago or so, which is the state sync part of our consensus. So I guess without further ado, let's dive into state sync. And to kind of like bring back into focus what we've already managed to forget, we'll start with looking at various constants in our journal, which determine the pacing of state sync. Like you know, our journal on disk is a ring buffer, so it fits statically allocated amount of prepares, only 124 prepares. So a significant part of a state sync is deciding whether it is safe to wrap the journal around and start writing the old entries when you need to jump ahead, when you could still repair using repair protocol. Okay, so I think, oh, Toby, could you say hi to people?
Hey everyone, nice to be back.
I get so excited that it's finally my face and not your face on intro that I forgot to give microphone to you. Sorry about that.
No worries.
Okay, so I think we want to look at the result of inspect constants. Let's see if this works. Oh, yeah, right. You probably want to flip this to dark mode. Okay, and right, this doesn't. I need to pull, I guess, right?
To get the new one, the new updated inspect constant.
Yeah, I'm not sure. Do we actually have it here? Because maybe not, or maybe we do.
I think we should have it. Should have it.
Well, We have only 3 steps left until we, yeah, okay, perfect. Yeah, checkpoint schedule. So we have checkpoints, ops, journal slot count, trigger, prepare op max, prepare max, and checkpoint next. So okay, let's ask Toby why journal slot count. Like, Toby, did they taught you to count? Because I mean, like 9060, then 1024, then 959. It's should be the other way around. Oh, I guess, okay, I guess this is, okay, so this is like cardinal, this is, okay, no, now I can read it. So the 2 primary constants is that our journal is 1K entries long, and our checkpoint is slightly shorter than that. So our first checkpoint actually happens on op 959. Then 32 ops later, we have this checkpoint trigger. So this has to do with compaction, because by the op 959, we have all the checkpoints data in memory, but it takes us 32 more ops to actually write it to disk. So only at this later op, we can update the superblock to point to the new checkpoint, because only at that later op we can be sure that all the data is safely transferred from write-ahead log to our storage. And I feel like I should make an SQLite joke here, but I don't know about that, so I'll skip it. Okay, now what is going to be interesting is that like our checkpoints are somewhat asynchronous. So while we are still saving this checkpoint to disk, we could still prepare entries later than the trigger. We can prepare them up to prepare max. I think this is actually conservative. I think we could, while we're still on this checkpoint 959, I think we could prepare all the way up to the end of a journal. So presumably we are more conservative here. But what we cannot do is that we cannot always acknowledge those prepares as prepared. We cannot always reply with prepare OK. So if we get a prepare number 998, we prepare it and reply prepare OK normally. If we get prepare number 1005, we write it to journal, but we don't send an acknowledgement. And this is what drives state sync, because when we see that the prepare at least 1000 was committed, we know that there was a quorum of replicas who acted prepare. But that means that we have a quorum of replicas who are already past this checkpoint. So that means that that particular checkpoint is durable, and it is safe to state sync to this checkpoint. Because remember, our core state syncing invariant is that data in IronBeetle comes in 2 forms. It can be in a form of prepare in a write-ahead log, or it could be in a form of LSM tables in the grid, in the checkpoint. And the critical durability environment we maintain is that at any point, we either have a full quorum of WAL copies or a full quorum of LSM table copies. The full quorum here is 3 for replication quorum. So we always have 3 copies in WAL, or we have 3 copies in checkpoint. It is unsafe to have 2 copies in WAL and 1 copy in checkpoint. That by itself is not sufficient guarantee for durability. Because what would happen is that, so imagine one replica. So we had, imagine we start with like 3 copies in the WAL. We are before checkpoint. Then another replica moves to the next checkpoint. And it incorrectly reasons that, hey, now we have 2 in WAL plus 1 my checkpoint. So it's actually safe to erase the data. So it goes on and erases prepare from the WAL checkpoint. Well, now, if those 2 replicas who still have prepare in the WAL become partitioned, then anyone else cannot actually do a log repair because no one has those prepares. But because only 2 replicas are missing, we still need to get the cluster unstuck. So we could say, okay, if we cannot repair through a WAL, let's maybe just state sync to a checkpoint, because we have a checkpoint, right? But if that point, if replicas decide to state sync, they jump over to the next checkpoint, but before they sync the data, the replica with checkpoint now gets partitions, and the replicas with 2 prepares come back online, the cluster is still stuck. Because the nature of state sync is once you jump to the checkpoint, you can no longer jump back. So you kind of like, because you cannot flip-flow between the 2, this means that you need to maintain full quorum for either of them. And now that I've spelled this out, it actually feels that maybe we could relax this if we allow like regression on the state sync. Like, you know, you say, okay, I want to jump to the new checkpoint, but then you realize, hey, actually that doesn't work out. So maybe let me try back syncing from the journal. But it's unclear if that works. Anyway, it's kind of like sounds more complicated. So okay, going back to this prepare OK. If we see anything committed past prepare OK max, we know that this checkpoint is durable. And that means that it is safe to erase all the WAL entries before that point. Does it make sense?
Yeah, that makes sense.
Okay, so now let's actually compare that with what our comments says here, because maybe we are wrong. Because yeah, this is essentially the invariant. Okay, let's see if this is correct.
Can you say where this is again? Because for me it's so blurry again.
Okay. Fonts. How do I increase font size in Emacs? Text scale increase. Okay. Okay, so I'm going to miss even more keys than I usually do. So we are looking at constants.zig, and at the very beginning there is like comp time block beside VSR check below VSR checkpoint ops. Do you see it, Toby?
I see it in my own editor now. I don't see. I mean, it's crazy how bad the quality is with our screen sharing tool.
Yeah, I wish I could. Yeah.
I send you a screenshot just so that you can enjoy it later when you look at Slack.
Yeah,
It's amazing.
Yeah. So anyway, invariant. To guarantee durability, a log entry from a previous checkpoint can be overridden only when there is a quorum of replicas at the next checkpoint. This assert guarantees that when a prepare gets bumped from the log, there is a prepare committed on top of the next checkpoint, which in turn guarantees the existence of a checkpoint quorum. More specifically, the checkpoint interval must be less than the write-ahead log length, that is 1k, by at least the sum of LSM compaction ops, the 32, to ensure that the final batch of entries immediately preceding the checkpoint trigger is not overwritten by the following checkpoints entries. These final batch updates were not persisted as a part of the former checkpoint. They are only in memory until they are compacted by the next batch of commits. It as the first batch of the following checkpoint. And 2 times pipeline prepare queue length, rounded up to the nearest LSM compaction ops multiple. This margin ensures that entries prepared immediately following a checkpoint's prepare max neither overwrite an entry from a previous while wrap until a quorum of replicas has reached that checkpoint. The first pipeline prepare queue max is the maximum number of entries a replica can prepare and act after a checkpoint trigger. So this is like prepare OK max. So checkpointing doesn't start normal processing, referred to as checkpoints or prepare OK max. The second pipeline prepare Q max ensures entries prepared after checkpoints prepare max don't overwrite entries from the previous log wrap. By the time we start preparing entries after the second pipeline prepare Q max, a quorum of replicas is guaranteed to have already reached the former checkpoint. Okay, yeah. That makes sense, but again, I feel this is still too conservative, and that prepare max we should be able to extend all the way up to the journal slot count. Okay, now, okay, I think I want to still stick to the dark mode here, and let's see replica.zig on view. Yeah. Yeah, I guess at this point we kind of like roughly understand like this critical invariant that we want to understand when a checkpoint is durable, when it is present on a quorum of replicas. And the way we understand this is by observing prepare OK messages. So prepare OK message carries 2 bits of information. It is acknowledgement of a specific prepare, but it is also an acknowledgement of specific checkpoint. So that's why we kind of like style our prepare OK messages until we got through a checkpoint. And maybe it makes sense to actually make those 2 messages disjoint. maybe actually we should separately count prepare case and for the purposes of OK and prepare, and prepare a case for the purposes of OK and the checkpoint, but we don't do that currently. Okay, so the critical decision to the checkpoint happens in the onView message. And we have this onView set checkpoint method, and it's amazing that LSP works in Emacs. So we have this onView set checkpoint method, which says, hey, we get a view message from the primary, which tells us where the primary is at. And so it contains primary's head up, and it contains primary's checkpoint. And if this thing returns true, that means that we want to state sync to the next checkpoint. So I think last time we kind of like covered this like far behind and like likely stuck messages in sufficient detail, so we don't have to do this. Do you have any memories about that, Toby?
Yeah.
Yeah, I remember that you understood it better than me. So anyway, if it looks like it is a good idea to checkpoint and we aren't already checkpointing, we say it's a good idea to state sync, and we aren't already state syncing. We say, hey, we now store this message as an authoritative source of information which checkpoint we are going to need. And this is tricky because physically state syncing is an asynchronous operation. So there is like three things we need to juggle. First of all, why are we state syncing? Well, we probably state syncing because we got stuck trying to run repair. What does getting stuck physically means? Well, there are like two cases. The easy case is that we realize that, hey, we need to commit a certain op, say op number 92, but we don't have this op locally, so we try to repair this op from someone else, and no one is replying to us with this op, right? That's an easy case. But there is a harder case. If the data we are missing is not the prepare, but actually a part of our LSM tree. So imagine that we did state sync successfully, right? So we have this checkpoint logically, but we are lazily repairing our LSM. So we are in the process of committing, right? And we are running compaction. And for compaction, we need to read a certain LSM table, which we haven't synced yet. So effectively, we are, quote, quote, blocked in grid read sectors call. Compaction told grid to read block, and that told storage to read sectors, and that is waiting for those sectors to get fetched from a different replica. So that's what we have. But what is the rest of the cluster? Well, the rest of the cluster turns out is much faster than us, and the rest of the cluster is way, way ahead. So the block which we try to repair, is not available. So essentially, we are stuck in these blocked call to read sectors. So that's kind of like our first concern, right? We like somehow need to get ourselves unstuck. Somehow we need to say, hey, let's stop trying to complete this compaction, because we know two facts. Fact A, that this compaction can no longer be even finished, and fact B, that actually there is a future checkpoint which we can leapfrog to. Okay. The second concern that we need to keep track of is that we need to physically state sync, which means that we need to, in our superblock, we need to replace the checkpoint. So checkpoint essentially is like a root pointer to LSM tree, right? Because our LSM tree is deterministic across all replicas, that means that we could implement state sync logically very easy. We just flip the root pointer. And we don't have the data this root pointer points to, but that's what our block repair protocol gives us. But still, we need to update this superblock with this new checkpoint. And that is also like asynchronous write operation. And while we are updating the superblock, like, you know, we might receive a new checkpoint, which might be even a better candidate for state sync. So we need to care about concurrency. Finally, we have our in-memory view of the journal. So remember, journal is 1K slots. That is 1 gig of data. And we don't store 1 gig of data in memory. 1 gig is all on disk, and we only cache like 16 entries from those. But we do store all the headers, because while the prepare is 1 megabyte, a header is 256 bytes. So prepares is 1 gig, but headers is 256 times. It's like a quarter of a megabyte. So those headers we store in memory. When we state sync, we obviously jump ahead our checkpoint forward, right? So we also need to update those headers. But we need to update those headers such that they are updated in a lockstep with our superblock, with our checkpoint on disk. Because if they are kind of like unsynchronized, then we'll trip all kinds of assertions, which verify that our log actually is anchored below at the checkpoint. So that's kind of like the three things we do when on view set checkpoint returns true. We need to cancel any pending grid IO, which might be blocked. We need to update our superblock with a checkpoint, and we need to update our in-memory view headers with headers. We'll start with cancellation, because that's the first thing that happens. But before we start with that, let me briefly discuss this checkpoint and superblock update. So for here, view, do we have a view message? View message, yeah. So the linchpin in the protocol which like holds this whole thing together is the view message. View message is authoritative information about the current view. And view is state plus events. It's log plus the checkpoint. So what view message contains, so this is the header. In the body of a view message, we have checkpoint and a list of headers. Okay, let's see. View checkpoint. It should be somewhere. I don't remember the name, sadly. View message. Yeah, a view message headers, a view message checkpoint. So once we receive this view message, we could get the checkpoint state out of it, which is like the first checkpoint state bytes of a body. And we can get slides of headers, which are like all the bytes after the checkpoint state. I realized. Oh no, text scale increase only works for a single buffer in Emacs. Sorry about that. Okay, but I mean, given how blurry that is, I guess it doesn't really help you.
No.
Yeah. So right now I'm looking in replica.zig at functions called view message checkpoint and view message headers.
I got it.
Yeah. So that's essentially I wonder if I can share like Emacs directly, like like there must be some extension to like see my cursor and like follow me. But well, it's like it will. We'll need another episode for configuring Emacs, I guess.
We could go to the server and Emacs.
Yeah. Okay. So the bottom line here is our view message contains headers and checkpoint. You've seen that when we decide to do a state sync, we store view message persistently on a replica. Then we cancel everything, which is asynchronous, because cancellation is always asynchronous, because during cancellation you always need to wait until the work is actually canceled. Then you do superblock update, which is asynchronous because it's a disk write. And after superblock update finish, at the tail end of that, you take this view message which you stored and you apply the headers from the view message to your in-memory state. Okay. Let's see the cancellation path. So where do we actually yeah, we have this function sync start from committing, which triggers the cancellation path. So specifically, like we don't need to cancel everything. Like if we are writing something, right, then we could just finish writing that thing, because writes can never fail. It's only when we read some data that we need to cancel it. So for example, if we are in the process of checkpointing, I think that is like writing data, and that will just write out. So we'll wait until the checkpoint is finished, and then I guess we'll resume our statesing if needed. The interesting part is if we are prefetching or compacting. So those are reads. The prefetch read is you read something from disk to execute, like you fetch an account, and compaction is compaction. So this we might need to actively cancel. We do this by calling grid.cancel. And this recursively triggers cancellation of everything that is happening everything is currently happening, so prefetch or compaction. And the contract here, like, when you execute operation normally, you send a callback. If stuff is canceled, then that callback just isn't going to get called. And I'm actually curious, what do we do with reads which we have submitted to IOUing? I guess we should wait for them, right? So yeah, I guess this is this is what I expect happens in the grid. So grid has a list of requests which are currently executing, right? Or should be executing, but they might not actually execute because grid is also component which tracks repair from the network. So basically, when a request comes into grid, it first adds into the queue, and from that queue, it could either go through IOUing to disk, or it could wait until it is resolved by some network request. So I think what happens is that we immediately clear all the queue, you could see it right here inside grid's cancel. We have this grid.readqueue.reset, which empties this out. But we might still have some outstanding IO submitted to the kernel. That IO, I think we actually wait for. So that's why we set grid callback to cancel, but we aren't actually calling this callback just yet. And then if you look at storage.read, so when we read sectors, we do read block callback. Yeah, and in that callback, we say, okay, if we actually cancel this, right, then we aren't going to call the callback for the actual read. We go in cancel join callback. And cancel join callback checks if nothing is executing. And if nothing is executing, then we call the cancel callback on the grid itself, which for the replica would mean that we verify something and then continue with our state sync flow. And actually, I don't understand why we do onView set journal here, because I would expect that that would happen after we write this for block. Well, never mind. Okay. I'm curious, where do we cancel the state machine? Because I think we also should have state machine for Oh, right. Okay. So I was wondering, grid. So we have state machine, right? Inside the state machine, we have LSM tree. Inside LSM tree, we have grid. So I was wondering why we do not cancel the state machine. That is because we only cancel grid, and the contract of grid is that it just drops all the callbacks on the floor. And then we just reset the state machine, and we reset the compaction. So kind of like we don't do the ownership hierarchy is state machine, LSM, grid, but we actually cancel the bottom layer, which is asynchronous cancellation, and everything on top of that we just reset. So if you look at, for example, compaction, reset. And this compaction reset is what is ultimately triggered by the state machine reset, right? It will just go and literally restore all the resources which are currently executed, because we know that, hey, after we canceled the grid, nothing will call the callback, so nothing will actually use those resources. So it's like fine to completely reuse them. I kind of like my explanation is like very muddled here. So I guess it's time for me to ask Toby if you understand anything.
I understand it. I think partially. I think I'm not 100% sure how the state machine cancel now works and when it's actually called. But I also have, I think, a more high-level question.
Yeah.
Like we do state sync, and so you mentioned these 3 steps, and we installed a new root, basically, like our new super block. But then we still miss the data, right?
Yeah.
Potentially.
Yeah.
And so when are we allowed to participate in commits?
Do you understand how we get the data back?
Yeah, so we basically, I mean, either we scrub it, potentially, or we actually do compaction and we read it, and then we don't find it locally, but we don't return errors or something on read, I think. We basically just try to get it from another replica, and this is actually the block, like the things that the repair basically the LSM.
Yeah, precisely. And not only during compaction, during normal commit path as well. Like, you just state sync, you want to process transaction, you want to know how much money there is on like Toby's account. You try to read block which contains Toby's account, and like it's corrupted, quote, on your local disk because you're not state sync, so you transparently repair it. So
basically you tell me that you can immediately start committing.
Yeah.
But what I wonder is, like, you might still miss some blocks that you didn't touch.
Yeah.
Do we run into problems that we are under replicated? Because
well, after heroically battling with Whopper over like 1 million Whopper bucks, no, we do not suffer this problem. But that thing that I'm hammering, that we have like this core safety invariant that either wall is replicated or LSM is replicated, is exactly the learnings from that Lone and Adder's Whopper battle.
But I don't understand it, because how do we know this? Because we basically installed a new checkpoint, we participate in committing, so we have the val, but there might be a block that we didn't touch. And other replicas also might not have touched this block. So it might be gone, right?
Yeah. So Let me see where it is. It should be here. Yeah, okay. So, inside
What are you
our
looking at?
I'm looking at superblock.zip.
Oh, yeah.
What do we store in a superblock? And in a superblock, we store the SR state, which contains the checkpoint state, and checkpoint state is deterministic across all the replicas, and the SR state, like everything else, which is specific to the replica. And in the SR state, we store sync op min and sync op max. So if you currently are at op number 100, and you realize that, hey, cluster is far ahead, and you want to jump to op number 200, you store 100 and 200 as sync op min and max. And the semantics there is that these two ops exactly bound the range of data you must be missing. You may be missing. So if you say, so imagine you sync op min is 100, sync op max is 200, and your op is your current head op is 250. Well, you know that any table which was created by ops between 200 and 250, you have fully intact on your disk, because you like actually executed all those ops, right? So you actually like this might have required you to run repair protocol to like get data for compaction, but you did that, and the new data, like, you know it is there. You know that the data older than 100 you also have, because that was before state sync. It's only the data between 100 and 200 which might be missing. So there is a scrubbing process, and the scrubber prioritizes scrubbing tables in this op range. And once they are fully scrubbed, you will update in your superblock this range saying, hey, actually, no, this now is fully synced.
How again do we know which tables are in this op range?
So information about all the tables is stored in the manifest. So just like we just know about all the tables, meta information about all the tables in memory. Information about the table obviously includes, like, you know, the address and the checksum of the index block, like what is like how to find the table. But it also includes the op number which created this table. So like when we compact something, during compaction, we like stamp the newly created table with the current op.
But if I miss the data, then I have maybe not created this table. So how do I know, like, how can I scrub it?
I mean, you do have, that's interesting. You do have all the tables in memory, even those tables which you do not have. Like, you might not have the table, but you do have the meta information about this. Because, kind of like epistemology. How do we know the set of tables we should have? They are stored in a manifest log, right? So manifest log is a linked list in our grid, which stores like add this table, remove that table. Okay, let me pause here. So let me kind of like get back to this cancellation point. So when we cancel the grid, right? Then we reset state machine. So we return the state machine to exactly the state it had when we started the replica. The next thing we do is that we open the state machine. So we ask our state machine to go and read the manifest log from disk and reconstruct the in-memory manifest. But manifest log stored in, I mean, this is beautiful. It's stored in the same grid. So after you state you actually don't have manifest log, right? So you go and start repairing the stuff. And by the time you open state machine, you know that, hey, actually you do have all of the tables present.
Oh, that's really cool, actually. It's like that is all the way down from the root checkpoint.
Yeah. So you have this sync-op mean, sync-op max. You know which tables you should be scrubbing, and you know once you scrubbed all those tables that you could kind of like reset this to zeros or whatever is the neutral value. And this is where this checkpoint schedule comes in. Because remember, like, so, okay, I've lost my Emacs. So this sync-op mean, sync-op max here is information local to the replica, right? So replica knows when it has all the data or when it might be missing data. But the replica also needs to somehow communicate this to other replicas. In particular, it is critical if the replica's checkpoint is not healthy to communicate to the rest of the cluster that, hey, this checkpoint is not healthy, so you might want to stall the processing until I am fully repaired. Because ultimately, this is the behavior we want, right? If normally we want to continue the cluster going ahead as long as it has durability. But if actually durability is missing, we do have to wait until this ligand replica fully repairs until it catches up. Because otherwise it might be unsafe to continue. So we somehow we need to communicate that, hey, hold on a second here. And this is where we remember that our prepare case also carry information about which checkpoint is durable. So the rule here is that if the replica has non-zero opsync mean, opsync max, then it avoids standard prepare case for the critical interval where those prepare case signify that the checkpoint is actually durable. But then again, it still provides durability for the journal. So if it learns that the checkpoint it doesn't have is present on the quorum of other replicas, it can safely continue sending prepare OK messages.
That's really cool, actually.
Yeah. And it was really cool to also discover all those invariants, because right now I have a fairly crisp picture in my head what actually should be happening for this to be correct. But when we were implementing this, we had to discover all those stuff, right? We have to reason backwards from a particular VOPA failure to understand why that thing happened and to reason backwards to invariance to understand like what actually breaks the algorithm. Okay, so I guess that answers your question about like how do we deal with data partially available? How do we make it safe? Okay. So yeah, after grid is cancelled, then we could where do we do sync superblock update start? Sync superblock update start. Okay, yeah. It's kind of like I'm not a huge fan of like saying dispatch because it makes it harder to understand what's going on. But yeah, so after we cancel the grid, so while we are canceling the grid, we still are effectively on the old checkpoint. Our in-memory state, our on-disk state is the same. The only thing we did is that we made sure that we will never ever call any more callbacks on all write IO, and we waited out all the existing IO to finish while not calling callbacks. So kind of like the IO which was submitted, it happened, we just didn't get the callback. So
I have a quick question here.
Yeah.
Just because I sometimes have these pathological cases in my mind. So what if like some other replica is state syncing from us while we discover that we are also behind, or so the other replica is even further behind, it state syncs from us, and we then start state syncing from someone else, and we cancel all IO. That means we don't respond, right? But I think we how do we do this actually? Can this actually happen? No, I think not. Maybe.
I mean, no. It can happen. Like you could state sync from a state sync. One thing to understand is that state sync is like atomic, in a sense that state sync happens once you updated the superblock, right? It's like very lazy. It doesn't like state sync doesn't require transferring all the data. So once you receive a view message which made you decide to do a state sync, that state sync will happen. It will take some time to like wait for all IO to finish or to get canceled, but it can no longer be blocked. And then like after that thing happened, you are essentially like, there is no state sync in state. It's just normal state. So from that you could continue state syncing. So it could be the case that yeah, you started state syncing, right? But then the cluster ran ahead, and that means you are stuck. So you're trying to compact something, you try to repair the data you need for compaction, but the data just isn't in the cluster. But at some point you learn that the cluster is on a further checkpoint than you are, and then you will go and state sync to that checkpoint. And in terms of sync of mean and sync of max, you will keep your old sync of mean, you will just update sync of max. So you will then have to like double check like that entire range of operations.
And can it be that I want to state sync? Say I state sync from you, but you also state sync, and so my state sync is not successful. You meant it's atomic, but it can be cancelled. Like, can it be unsuccessful because you moved on and don't have the checkpoint anymore, or how does this?
Well, I mean, When I say state sync, I mean logical state sync, updating your superblock. And that is asynchronous and atomic. It is asynchronous because it is a long, delicate dance of canceling the work, waiting until the work is canceled, and updating the superblock. But it is atomic in a sense that once you receive this view message, and
I always forget that the view message is everything you need to update the superblock, right?
yeah.
Or do you need something else from some other replica? No, only the view message.
Yeah, so this is like the serialization point. Self.sync view equals message.ref. So once you've done that, you fully logged into this state sync. Like, it will take some time, but the time is guaranteed to be bounded. You will only have to wait until essentially all IOs submitted to your local disk finish, and those cannot like fail. I mean, they can fail, they cannot run indefinitely. Yeah, and after that, like you will change to that view. So it's like, yeah, you could totally do like state sync and state sync and state sync and state sync. The only thing here is like, you know, like in the line above, like you see, if self-syncing equals updating checkpoint, return true. So if you are at that point where you're updating the superblock and you realize that, gosh, you actually want to jump even further, you don't do the jump. But then, like, you know, at some point later, you will realize again that you want to state sync and you again jump over that.
Okay, that makes sense to me. That's actually good.
Okay, so let's kind of like continue from where we left off. So we said grid cancel and passed the callback. Grid cancel immediately cleared all the read queues, all the write queues. It then waited for all IOs already in kernel to finish, and then it calls this callback. So at this point, we, I think, are in slightly indeterminate state, in that our grid is dead, effectively, right? But the state machine and the compaction on top of it, they are like right in the middle. They are frozen in time. Like compaction is like trying to do, it just doesn't yet know that it will never ever get the callbacks resolved. So at this point, we do this sync dispatch, and we say, hey, now we want to update the superblock. And we start our updating the superblock. And that basically says, hey, why? Okay, Emacs is weird, or maybe I'm weird. Okay, yeah, this is, how does it work? I don't get it. Okay, I get it. This is complicated. So, remember what you have said, that, hey, we have like the checkpoint, right? And then we have an in-memory headers. and we want like to kind of like update them in lockstep. So the thing is, in the VSR state, in the superblock, we store not only the checkpoint, but we also store the headers. So there is like a tiny like suffix of headers we store directly in a superblock for redundancy. Why we do that? Well, we'll understand how we finish when we finish the view change protocol. So when you update the superblock, you actually want to update simultaneously. So you kind of like want to update on disk checkpoint and headers, and also in-memory headers. So this is like just tricky control flow. The process starts with sync superblock update start. And this is where we wait, what was there? Okay, this is where we exit that semi-indeterminate state. So before this line, before state machine reset, our grid is dead, but our state machine is frozen mid-compaction. Now we reset the state machine, and we say, okay, like just abort everything you do and just reclaim the resources. So grid cancellation is like a gentle communication protocol, right? We ask grid, hey, could you please cancel? And once you are done, can you please call back using this function? Reset is just synchronous. Doesn't matter what you've been doing, like reclaim all the resources. We do the same for preset, client stations, whatever. Crucially, state machine reset is also the thing which resets our manifest. So after reset, manifest is empty because we don't know what actual tables we should have. And to get that manifest, we need to do this process of reading the write-ahead log from disk, which is state machine open. Okay, so now after this resets, we are like in a well-defined state. Then we call on view set journal, and this is why I hate this control flow, because we call sync dispatch. Sync dispatch calls sync superblock update start, and then we go back to on view set journal. So on this view set journal, what we do is that we where it is, yeah, we replace the headers. So we take the header messages in the view message and we just install them into our in-memory log, which we do according to the rules of a view change protocol, because we might also, and this what makes this like extremely tricky. Sometimes we need to do a view change and the state sync at the same time. We might like want to say, okay, I want to state sync without view change, or I want to view change without state sync, but that's not always possible. Because imagine you've been partitioned from the cluster, right? And then you rejoin. So the cluster is obviously on a higher view. So like you could learn the checkpoint it has, but it's not from your view. And now you kind of like cannot really install this checkpoint because, well, if the checkpoint is the higher view than your view, then it's like obviously like some like a violation of a very core invariant that the replica is not aware about the future views, right? So you would think that, okay, can I first view change and then checkpoint? But the problem is, one of the invariants of a view change is that if you are in a view, then you have a log consistent with this view. And if you have a log consistent with this view, this log must be consistent with your checkpoint. And that's kind of like just not possible if you are on a all checkpoint. So that's why you kind of like want to do this in a lockstep. It's going to be for the next episode to understand how specifically we change like our view headers, but kind of like the bottom line, like we figure out which write headers we need to install, we install those headers. And then if we are state syncing, so if we have this checkpoint, we also need to install if we are state syncing, we call self view durable update. And view durable update is bad name because it's not the update of a view durable. So view durable is a single number in a superblock. It actually updates the entire superblock. So this view durable update will update the superblock with the new checkpoint and the new headers. And this is this asynchronous operation. So we have here superblock view change, where we pass in new checkpoint where we say, hey, this is our sync op mean, this is our sync op max, and then we pass the callback. So after this callback, we are in kind of like well-defined but useless state. So our state on disk is correct, right? Our VSR state in memory is also correct. So we are on this new checkpoint and our log is consistent with it. But our state machine is still in this reset state. We don't know which trees we have. So that's why we call sync superblock update finish. And here, I think we should call grid open. Yeah, we first call grid open. So like even before we go to the manifest, one other thing we lose is we lose freeset. Because freeset is also stored in grid, and freeset is also part of a checkpoint. Because, like, you know, before the state sync, we had some tables, right? But after state sync, those tables might actually be free space on all other replicas. So we actually need to learn about that. So this is what grid open does. Grid open reads freeset from the disk so that we know which blocks are free. And after we open the grid set, we open client sessions, and we don't talk about client sessions because that's not really key to the protocol. But after the client sessions, we should be, why scrolling doesn't work? Yeah, we finally call state machine open. So state machine open, normally we call it during startup, right? When you start, you like read your journal, do protocol aware recovery on your journal, what I covered on like the previous episode. And then you call grid open to figure out this free set, and then you call state machine open to read manifest log and reconstruct your set of tables. Exact same thing happens after state sync. So state sync is literally we kind of like update the superblock, and then we just reboot the replica. Except that we don't reboot, we like just redo it. I think at some point we actually considered that maybe we need to implement state sync by like powering on and off. And I wonder if that might still be a good idea. Well, I expect Slack messaging coming. I have some crazy ideas here. Okay. So yeah, after the state machine opened, we basically are happy to continue participating in the consensus. And I think even before the state machine is open, we already are happy to provide durability for the journal. So we already can append, we already can prepare OK. The only thing we cannot do is that we cannot commit. Yeah, because if you try to commit and the state machine is not open, we just say, okay, we can't commit until the state machine is open. But yeah, so I think actually, Toby, I think that's it. I think you now fully understand how state sync works, and more importantly, why the thing we do is correct. Why we actually guarantee durability at all time. And at all times.
Yeah, that was really cool. Now, finally, the mystery is solved in my head.
Okay, perfect.
How we make sure that data is, even though we recover lazily, I mean, kind of lazily, we are still fully replicated. I mean, not fully, but more than enough replicated.
Yeah, we could check this sync grid done. Yeah, so well, I think there is like one detail here. So I think originally we had constraint that a replica that replica could only update sync op min and sync op max using in-memory state. So if you are in the middle of state sync, right? In the middle of scribing for state sync, and then you crashed and restarted, you would have to start scribing from scratch. I think we actually fixed that, maybe, such that we could now like incrementally update our op min on op max. So we start 120, but once we did 150, we remember that 150 in our super block, and if we restart from that point, we don't have to redo that work. Or maybe we don't do this. I actually don't remember.
I will look it up. I'm interested now.
Okay, yeah, I think that's it. Are we happy for today? Are we ready to call it a day?
Very happy for today. Also happy to call it today.
Yeah.
But
okay.
It was really cool.
Yeah. Okay. Could you do wrap up for us then, Toby? You are full screen now.
Yeah. So thank you for watching. Now you know how state sync fully works. At least if you also watched the previous episodes. Otherwise, you partially know it. And see you next Thursday, right? At 5 p.m. UTC.
Goodbye.
Goodbye.